Okay, so last class we talked about the problem of best fit line and the more general best fit subspace problem. Okay, so what we'll do today is kind of, we settled on some formulation, some quantitative way of formalizing the problem, and then reviewed some linear algebra basics around how to solve it. So what we'll do today is kind of make further inroads on how to solve this best fit subspace problem. And this will lead to this very important idea in representation learning or compression, which is principal components. And then hopefully from there to a closely related problem called low rank approximation. Okay, so that's the goal for today. And a couple of announcements. Assignment 2 will be out today at 6 p.m. on Gradescope, so you should be able to download it and review it. And assignment 1 grades have been posted. Okay, so if you have any questions about the grading or any regrading requests, please just submit them in a week. Don't submit them the day before the final grades are due and say, oh, in assignment 1 there was something missing. Okay, just keep things current so that everything is in memory. Okay. All right, so what did we talk about last time? So we were looking at the following problem. So we are given as input some data set, right? Just recall the notation. So we have x, which is x1 through xn. These are all d-dimensional points. As I said, even though we are visualizing PCA typically in small dimensions, it only really makes sense in very, very big dimension. You think cases, cases where d is like maybe 1,000,000, and the number of sample points is much smaller, like 100K. Okay, so that's the setting where it's most interesting. And our goal is to find a line and eventually to find a subspace, right? That minimizes the error of the line. So we once again have some kind of optimization problem. We have a concrete error function that we are trying to minimize. Okay, so this is the error function. Okay, so one thing is, somehow, what are we optimizing over here? We are optimizing over lines, right? So we need some way to parameterize lines, and that will show up in a little bit. So once we have some way of, some parameter space that we're optimizing over, we can talk about, okay, what algorithms can we use? Our favorite algorithm, of course, once you have an optimization problem, is to do gradient descent. We'll talk about that as well. Okay. All right. But first, I want to massage this cost function or error function into something that is a little more amenable to any of the algorithms that we have, right? Right now, it has this complicated form. Okay, I have this point, I'm projecting onto the line, and so on and so forth, right? But you can simplify it significantly. And the reason we can simplify it is, we had these properties from last time, right? I think we just need these two, so let me copy them. call. Okay, so we have these two things. So in particular, if we use this Pythagoras' theorem here, so this is what we are trying to minimize, right? So I can write it effectively as okay, so this is our cost function. And if you use the Pythagoras' theorem, I can rewrite it as okay. So as we discussed, the angle is 90 degrees, so you can apply Pythagoras' theorem. This holds more generally for any subspace, so in particular for a line for sure. And what do I gain from that? I can write this as okay. And now two things happen. One, so remember, the data set X is fixed. And what we are optimizing over is the line L, right? We're trying to find a line which minimizes this error function. But the first term here doesn't depend on the line L, right? So this is the same for every line that you choose. So that means finding a line that minimizes is the same as finding a line L that, and we have a negative sign here, right? So we want to minimize the error term, and this doesn't depend on L. So we should be maximizing this term. Okay, so both are equivalent. Quantitatively, there'll be differences, but we're only interested in what line achieves the optimum. That's more important than what's the actual value of the objective function. We are really interested in what parameters give us the optimum value. It's the same as finding a line that maximizes okay. All right. And this is the version which is a little more easy to set up as an optimization problem. So let's give this term a name, and I'm going to call it the variance of the data set restricted to that number, right? So this is just summation of all the points of the lengths of the projections. Okay. So intuitively, you have your, so let's say this is what my data set looks like. Now, we can imagine drawing some lines, right? Let's say this is one line. And I can also draw like a line like this. It's not 90 degrees. Let me make it just so that it's clear. Okay, so this is the other line. Now, if I project along the blue line, the points are all kind of, much farther, much more spread out, right? The lengths of the projections are much, much higher. Okay. So if I project out, then I get something like this. And if I use the red direction, what do I get? I get these points. Kind of, the projections are all much closer to the origin. Oops. Okay. So which line do you think has higher variance term? The blue or the red one? the projections on the blue line have higher variance because they're more spread out, right? So intuitively, we are looking for a line which has the most, when you project along that line, the data set must be most spread out. Seems a little counterintuitive that you're looking for this, but the intuition is that you're looking for a line where the data is most spread out so that you can capture most of the information by just looking at that. Okay. So if all of the points are, for example, very close to this blue line, when I project down the perpendicular direction, they're all close to zero. So I'm not learning as much information about the data set by this projection. Okay. So that also makes a lot of intuitive sense. Right. And the same argument really also works for high dimensional case. So just as we did it for a single line, we can also do it for a subspace. So variance, you can define a similar term, which is just this guy. Okay. So in general, so we have this equivalence. Finding the subspace S to minimize the error is equivalent to finding subspace S to maximize the variance. Okay. All right. So we are looking to find this subspace which maximizes the variance. But how would we parameterize the subspace? When we think of, like, let's say when we were doing optimization earlier, we said we have a vector, we're doing some unconstrained optimization. I can do gradient descent and so on. So even if you wanted to do that, what are the parameters here? How would you describe a subspace to somebody? So what does it mean to find a subspace? Any guesses? Yeah. Yeah, and ideally, because we are looking at, you can find any basis. Technically, any basis would be good, but just for computational purposes and the way the algorithm works, we are actually going to try and find an orthonormal basis. Right? So we are going to target finding an orthonormal basis for the subspace. Okay, so that's our goal. We'll get there very shortly. But first, again, let's focus on the line case, set up something, and then we'll do it for the subspace case. Okay. And for the line case, how do you specify a line? It's basically just span of a single vector v. Right? This is just like lambda times a vector v, where lambda is any number on the real line. Okay. All right. So our parameter space is is this directions v, but as I said, we're going to normalize things. So we are really looking for v, which are unit vectors. Okay, just so that we don't have redundancy in how we are representing things in the parameter space. And it's especially helpful when we do the subspace case. So let's say this is our data set once again. Okay, and maybe I pick this as my first line. So I pick a unit vector which describes the entire line. There is still some redundancy in that the same line can be represented by two unit vectors. Right? I can either pick this direction or the negative of the direction. Both describe the same line. Right? So in some sense, there is no unique solution to this problem. When we say a representation, give me a v which gives me the line, there could be different v's that give the same line. The same way, when you want a subspace, I can have different orthonormal bases, which describe the same subspace, right? It doesn't matter which basis you find, any basis is okay, right? Okay, so we have this V, and let's think of what are we trying to do. So we have this point X, and we want to look at the projection of X onto this line. Okay. Now the question is, what is projection of X onto the line? We saw this formula before. So L is the span of V, and we can assume V is a unit vector, but even if not, let me just write it down, what happens. So what's the general formula for what the projection should be? Well, let me just state what it is. So the projection is obviously along the direction V, but what is a scalar multiple is given by the inner product between X and V, right? So this is some formula that we discussed a long time ago. And in general, this is what you get. Okay. So this is the exact formula. So if V is a unit vector, then it's just you pick the unit vector and multiply it by the length of the projection, which is just the inner product between X and the unit vector direction. Okay. And a corollary of this simple fact is that the projection of X onto L, the length is essentially determined by the inner product. Okay, it's the inner product scaled by the length of the vector V. Okay, if we assume the absolute value, sorry. If you assume V is a unit vector, then it's just the inner product, right? Okay. So, we can write it either as a constrained optimization problem where V is restricted to be unit vectors, and then you have no V, just the inner product squares, or an unconstrained optimization problem where you divide by this norm V squared. Okay. Both are really equivalent. It doesn't quite matter. So in general now, if I have, I can write down this compact thing for what the variance of the data set is. Right? This is just summation I equals 1 to n x xi comma v squared divided by the length of v squared. All right. Now this still looks a little bit messy, but we can actually write it in a much better way by writing it in matrix form. So imagine I write down a matrix where each row is one of my data points. Okay. And as I said, we should really think of the setting where the dimension is much, much more than the number of points that you have. So it's a, wide matrix instead of a tall matrix. Okay. And what happens if I multiply it with the vector v? I get a new vector. What are its coordinates? It will have n coordinates, and the first coordinate is basically the inner product x1 comma v, right? Which is what's showing up here. The second coordinate will be x2 comma v, and so on. Okay. And let's call this, data matrix X. Right? So X is just a matrix, comprised of where the rows are just the data set points. Okay. So what does this mean? What do we end up with? We end up with a very compact formula for the variance term. So the variance of L, of X restricted to L is just the length of the matrix vector product X times V squared divided by the norm V squared. Okay. So this is our optimization, function now. I want to find a vector V which maximizes this ratio. Multiply my X with this vector V and then, look at the length as scaled by the length of V. Okay. All right. So we can summarize our new version again. So the best fit line problem is the same as the following. So we are given as input a matrix X, okay, which is n by d, and our goal is to find a vector V that maximizes this ratio. Okay. And as I said, you can either just look for a unit vector or something else. Scale always, right? And when you find a unit vector which satisfies this, we'll give it a name. The unit vector that a unit vector any vector that achieves this maximum is called a first right singular vector of the matrix X, or alternately, another name for it is the first principal component of matrix X. Okay, so now we can define it for any matrix. For any matrix, the vector V that maximizes this thing, any unit vector that maximizes this is called a first principal component of X, or the first right singular vector. It's called the right singular vector because I'm just multiplying on the right side. Okay. All right. Let's do a couple of quick examples to get a sense of this reformulation. I mean, so far we're just kind of massaging things from one formulation to the other. We still haven't discovered like a way to compute this. We're just getting there by writing it in some ways. Okay, so let's say a quick example. Now, what if my vector, my matrix looks something like this? 10 minus 1 and that. Okay, so let's say this is what my matrix looks like for whatever reason. Now, what is the first principal component? I want to say you don't even have to really compute anything. You can guess what the first principal component is. So what's the first principal component here? E1, right? So basically there's no variance in the entire points across the other coordinates, right? So it's just going to be 1, 0, 0, 0. Okay. And even when I don't put 0, if I just put another constant everywhere, you can still compute it in a similar way very easily. Okay. Let's do another example. What if it's just like, u, 10u minus 1u? Okay, so now all of the rows are just some, multiples of vector u. So what's the first principal component? Yeah. Yeah, it's just u by u. Right? So you need, the way we defined it is always a unit vector. So you take your vector u and scale it by its length to get a unit vector along its direction. Okay. So these are some trivial cases where you can just see and guess what the first principal component is. But in general, it would be more complicated. Right? Okay. So we have this very clean formulation of what it means for, what it means to optimize, what you need to optimize if I'm trying to compute the first principal component and hence solve the best fit line problem, right? But how about the case where I have a subspace? How about the subspace, best fit subspace problem where I'm trying to find the best two-dimensional subspace that explains my data set, right? So now recall, what did we have? Our goal was to minimize this. Find me the two-dimensional subspace, which minimizes the error, or equivalently maximizes the variance, which is okay. So let's say for now that somehow you found a way to solve the best fit line problem. Okay, I can find a single direction that I can find the first principal component. I can find the first right singular vector. Is there a way to use that to solve the two-dimensional case? Yeah. Yeah, exactly. So the intuition is that somehow, so recall what is our goal, right? So we have maybe this is our subspace. We have our set of points. Okay. And if I find a line that maximizes it, I can project all the points onto the line. Okay. So this explains part of the variance in the data set, right? So the intuition you should keep in mind is that I'm trying to find the two-dimensional subspace that captures most of the variance in the data set. So I found one line which captures as much as possible. What can I do to find the second one? Maybe I'll take out this first line and then do the same thing again, right? So intuitively, I'm just doing a greedy approach. I want to find two things together which optimize, give me the best variance. I'm just going to find the first line which gives me the best variance, remove it, and then find the second line which gives me the best variance. Okay? So recall, so the idea as suggested is to use a greedy approach. Okay, so find V1, the first principal component, and then we're going to take V1 out and repeat. Okay, so what does take V1 out mean? Basically, V1 explains part of the sample point X, part of each point Xi. And we're just going to run it on the error vectors that are left out by this direction. Okay. So, it's not the best picture, but hopefully it still makes sense. So let's say this is my line. Now, if this is my point, I can project it. Maybe let me use other color. So these are the error vectors. Okay. So I build a new data set, which is just this purple error vectors, and then run the first principal component algorithm on it again. Okay. So that's the idea for finding the second principal component. And I should say this is really a miracle of nature that this actually solves the problem. Greedy approaches usually are, they work sometimes, but most of the time they do not work. Okay? Potentially, you would have had to do some complicated optimization where you had to look for both directions simultaneously. Right now, we made it much, much nicer by saying, okay, I'll find the first one, that's easy. And then I'll find the second one, and then I'll find the third one, and so on and so forth, right? So whenever greedy things work, of course, it's very nice, but they need not always work. Okay. So in particular, okay, let me write that down. So the idea, we'll talk about why it works in a second. Find the first PC V1. Okay, we still have to solve this problem. Okay, we'll solve that in a second. But if we had this oracle, someone gave me the subroutine to find the first principal component, then I can do something. What am I going to do? You can either think of it as projecting all of the points, into the orthogonal space, or just subtracting and looking at the error vectors. Okay. Then I'm going to form a new data set, which is just xi, which is the error vectors. Okay. And, again, when you want to compute the error vector, where is this picture? Yeah. Okay. So this is x comma v times v. Okay, if v is a unit vector. And the error vector here is going to be x minus x comma v. Okay, so that's what we are using. So in this picture, v is a unit. Okay, and then find the first PC v2 of x tilde, which is x1 tilde, x2 tilde, so on, xn. Okay, and then we can repeat this. Right? So this is one way of thinking about it. Okay. The other equivalent way, which turns out to be more useful computationally, is that, okay, I found one direction which maximizes the variance. And so just thinking a little ahead, if I want a two-dimensional subspace, we said we are looking for an orthonormal basis, right? So that means, if this is my first vector in my orthonormal basis, I need my second vector, which is going to be perpendicular to V1. Okay. So either I can say, find the first PC V2 of this modified data set, or just somehow find me the vector which maximizes the variance again, but is perpendicular to what I've already found. Okay, that's another greedy approach. Again, it's a miracle that both of these are equivalent, but it's another greedy approach. I'm finding the orthonormal basis somehow one at a time. Okay. So another idea is find the first PCV1 as before, and then find the vector V2 that is perpendicular to V1 and maximizes. Okay. So in fact, this is a definition that is more useful for computational purposes, as it turns out. Both are really equivalent, but this is more useful. And in fact, that's what gets implemented because slightly better in terms of implementation. Okay, so the second principal component, we are actually going to define it this way. Is the second principal component or the second right singular vector of x is defined as the vector which maximizes essentially the same objective function as we had before, but with the additional constraint that it should be perpendicular to the first principal component. So, I'm using the shorthand, but okay. So I'm finding the basis one vector at a time. Okay. And if I ask you to find the three-dimensional subspace, the greedy approach would be either to repeat, you find the first one, take it out, find the first one again of the leftover, take that out again, find the first one of the leftover, and so on, or do this, right? Once I found V1 and V2, find me the vector V, which is perpendicular to what I've already found, and then maximize this. So in general, we can define if V1, V2, so on up to Vi minus 1 are the first, second, all the way up to I minus 1th right singular vectors or the principal components, then the ith right singular vector is any vector that maximizes the same thing, the same cost function, but now it should be perpendicular to every other vector that I've found so far. So I'm adding more constraints as I go ahead. Okay. So this means it's perpendicular to all previous. Okay. All right. And so I said 2 times already that it's a kind of a miracle that the greedy algorithm works. And just to give a sense, remember long ago, we had, we discussed how to define this error function. And we said, it makes sense to look at the distance of each point from, the subspace that you're trying to approximate the data set with and aggregate the errors, right? So we defined it as this guy. For each point, I look at the projection onto the subspace, and then we look at this. We looked at the sum of squares. But potentially, I could have defined something like this. While to aggregate the errors, why should I do sum of squares? I could just add up the errors. Okay, that's also very reasonable qualitative. Okay, it turns out that if you define it like this, the greedy approach does not work. And that's one of the reasons why looking at sum of squares makes the problem so much easier. If I do it this way, the greedy approach does not work. It might, even if you know how to find the first sort of best fit line when I define the optimization problem like this, I do not know, it won't give you a way to find the best fit two-dimensional subspace, three-dimensional subspace, and so on. Because the greedy thing won't give you all. Okay? So, if we had defined error this way, then greedy would fail, making the problem much harder. Okay, so a priori, both of them seem qualitatively achieving the same thing. So how do you make the choice? You really made the choice based on computational considerations like this. Okay. There is also a good statistical reason, but I would say the computational one is just as equally important. Okay. If you don't have the square, then the greedy algorithm would not work, and it's a much harder problem to solve. Okay. And you cannot find one vector at a time in this basis too. That will give a very suboptimal solution. You can set up a problem where looking at all directions simultaneously gives you much better solution than looking at one end. Okay. All right. So that's something to keep in mind when you are designing your sort of cost functions to capture your learning problem, whatever we have, right? So we have a good representation learning problem. There are various ways to formalize it, but only one of them really gives you something that you can solve efficiently. Okay. All right. So what I want to do next is really just show the following. I'll just show that the greedy algorithm works for finding the best two-dimensional subspace. Okay. And you can repeat the same thing for 3, 4, and so on. Right? So the theorem is going to be that the span of the first two principal components solves the best fit subspace problem. If I'm looking for the best two-dimensional subspace problem, I can solve that by first finding the first principal vector and then looking for the second vector, which maximizes this while being perpendicular to the first. Right? Okay. And as I said, the same proof more or less works for all k, but I'll just do it for k equals 2. Right? And how do you prove such a thing? Well, let's just first set up the problem in some suitable notation, and then it'll follow quite naturally. And you'll see why having the square here is critical for this argument to work. All right? Okay. The first principal, let's say V1 is a first principal component. Remember, this is a thing that maximizes X times V by V. Okay. And V2 is our second principal component. This one maximizes the same thing, but only among vectors which are perpendicular to V1. Okay. All right. So we want to say that the span of these two things, let me call it SPC, which is span of V1 comma V2, maximizes the variance. Among all two-dimensional subspaces, this is true. Okay, we want to say the span of V1 comma V2 maximizes the variance among all two-dimensional subspaces. Right, so this is what we want to show. To picture it, let's say this is a right? Okay, so this is our, let's say, this is V1, this is V2. Okay, so this is SPC. And now, maybe I have some point X here, and it has some projection onto this subspace. Right? Now, what is the cost function associated with this? We are looking to see this guy, which is summation I equals 1 through n, the length of the projection of each point onto the subspace squared. Okay. So we are interested in the length squared of this purple vector. Okay. And how can I compute the length of this purple vector if I give you the vectors v1, v2, and x? So, I gave you these vectors, and I'm asking you, is there a nice formula for computing this quantity? For a single vector, we saw it was just given by the inner product, but now I have a subspace. So how do I compute the length then? Exactly, right? So, again, we have to use some linear algebra that if I have any two orthonormal vectors, this is not particular to principal components at all. It's just for any orthonormal basis. If I have two orthonormal vectors, W1 comma W2, okay? And if I have T, which is the span of these vectors, W1 comma W2, then the length of the projection of X onto T, the square is just this. Okay. So this is the, kind of the high dimensional version of Pythagoras' theorem. It's just applied to, so let's say this is W2, this is W, maybe let me write it in a slightly different way. Okay, so maybe this is W1 and this is W2. It works for any orthonormal basis. It doesn't matter what basis you pick. If this is my point and I project it onto the space, then the length of the projection can be computed just by the sum of squares of the inner point. Okay. So we can use that. So that means the cost function that we're really interested in is this. Okay. Oh, this should be xi. All right. Okay, so I can separate it out and just slightly write it in a more compact way as the matrix x times v1 square plus the matrix x times v2, the length square. Okay, so we did this conversion already, so I'm just repeating. Okay, so once I have an orthonormal basis, the variance of x restricted to the subspace can be computed by this compact form. Okay, now what are we trying to say? We are trying to say that this SPC maximizes this among all other possible two-dimensional subspaces. So we somehow want to compare it to any other potential two-dimensional subspace and say this is higher, or at least as big, right? So how do I do that? I can pick any other two-dimensional subspace T. Okay, so let's say this is span of W1 comma W2. And I can compare, I want to compare the variance that you get from this. Okay. The same formula will work. So this is going to be just x times W1 squared plus x times W2 squared. And this is going to be x times V1 squared plus x times V2 squared. Okay. So we have these two things, and I want to say we want to claim that the principal component span gives you a higher number than W1 and W2. Okay. So how can I compare these two things? In general, we don't know anything about W1 and W2. There are any two other orthonormal vectors, right? I picked an arbitrary subspace T, and then I'm claiming, okay, you can make this comparison between any other subspace T and SPC. Okay. I want to say somehow that, ideally, we want to say this is less than or equal. Can we at least make some comparison between the two? What do you think? Okay, how about just these terms? Which of these two would be bigger? By definition, the V1 term should be bigger, right? So recall, V1 maximized. It's a unit vector. So among all unit vectors, it maximized this, right? So this implies that at the very least, I can immediately conclude that x times W1 squared is less than or equal to x times V1 squared. Okay, so we have sum of two things, and the first term on the left-hand side is smaller than the first term on the right-hand side. So we made some partial progress. Okay, but how about the second term? Yeah. Right. Exactly, right? So you have to be careful in picking the basis. Okay, so that's the trick. Because I cannot directly compare the second terms here and here, right? V2 doesn't universally maximize this. It only maximizes this among things which are perpendicular to the first principal component, right? And W2 need not be perpendicular. In fact, what if that is, V1 in the other case, right? You can pick any basis. So I can not just compare the two things like that. Okay, does it make sense? So ideally, we would like to say, okay, the first term is smaller than the first term, the second term is smaller than the second term, and I'm good. But that's a bogus argument, because V2 is only maximizing this under a constraint. Okay, so I cannot make this comparison between term by term. right? So we have to be a little bit more careful. In fact, we have to do it based on the subspace, all right? Okay. So, we cannot, by the same logic, we can, in some sense, we can say that x times W2 squared is at most x times V1 squared. This is fine, but that's not useful for us, right? I'm still comparing the second term to the first term, but, it's really this guy that needs to somehow win the battle for us, okay? But we cannot say okay. So how do we get around this? We get around this by this nice fact about orthonormal bases, right? So in some sense, when you have the subspace T, you can pick any orthonormal basis for it in our calculations, in our analysis, okay? For your algorithm, just give me any basis, I'm happy. But for my analysis, I can pick any orthonormal basis to kind of represent this subspace, right? And we are going to get around this by choosing the subspace a little carefully. So, okay, so let's say this is my subspace T. And T has nothing to do with the span of the principal components. They could be wherever they are, right? I'm trying to compare with any possible, this is W1. Maybe let me write a smaller vector. And this was my first choice of W1 and W2. I started with something like this, let's say, okay? And, maybe my V1 is right here. Okay. I'm looking at how the first principal component looks against T, right? But I'm not tied to this particular basis. I can change the basis however which way I want, right? And as suggested, I can rotate this orthonormal basis and still capture the same subspace. And I'm going to rotate in such a way that W2 is perpendicular to V1. So I'm going to say, okay, project this guy onto the subspace. Okay. And I'm going to choose the basis more carefully. I'm going to choose my basis this way. Okay. So now W2 is going to be perpendicular to V. All right. Does it make pictorial sense? I can choose any basis and do this calculation. And I'm going to be a bit more careful in how I choose the basis. Otherwise, I cannot do this term by term comparison. Right? Okay. So let me just write that down. Claim we can always pick a basis for T such that W1 is perpendicular, sorry, W2 is perpendicular to V1. Okay. And once I have this, I'm in good shape, because then and this implies that is less than or equal to x times v, right? By definition of the second piece. Okay. So now we can say the variance of t comma x is just x times w1 squared plus x times w2 squared. The first term is always true, and the second term is also true. Okay. And the same argument basically works for k-dimensional subspace. You just have to show that if you give me k-dimensional subspace, I can pick a basis where you have this orthogonality constraints all the way. All right. Any questions about this? I'm only doing the k equals 2 case, but kind of works for everything else. We just need a version of this lemma for the high dimension. Okay. All right. And in summary, the best fit subspace problem was equivalent to maximizing the variance of the data set. Okay. And which is equivalent to finding the first k principal components of x. Okay. The first k principal components of x will solve the best fit subspace problem for dimension k. Okay. Any questions? All right. So even to find, even among this, we know that we really just need to find kind of, either the first direction or some way to bootstrap it to find the perpendicular direction after. Okay. All right. So before going into how do I find these principal components, we still haven't solved that. I'm going to kind of, push this under the carpet for a little bit and talk about a different but closely related problem. Okay. If, when you look at it or hear about it the first time, at least there should not be an immediate connection, but it's a great blessing for us from linear algebra that these two are very closely connected. All right. Okay. So what is this other problem? It's called low rank approximation. So what's the low rank approximation problem? So intuitively, we're just given some big matrix, typically again, you can think of it as a wide matrix, or tall matrix, doesn't quite matter. Okay, so this is, I'm giving you some matrix X, right? We're not thinking of the matrix, we're not given the rows. In some sense, earlier, we're given these points, which were the rows of the matrix, right? So now the rows themselves might have some meaning, might not, but just think of it as you're given some matrix, okay? And think of it as like, maybe you have some cities on the left-hand side on the rows and some other cities on the columns, and you're trying to compute like each entry is the distance between them or the flight times between them or something like that. Okay, it can be pretty complicated. And our goal is to approximate this matrix by something simpler. That's all. So we're trying to approximate X by a simpler matrix. Okay. Why would you want to do that? There are many reasons, but one of the important ones is that often matrices like this are very expensive to even store. Okay, you might store it once, but if you want to manipulate them, then keeping them in RAM, etc., can be very expensive. So you have to do some sort of approximation to manipulate them. Okay, especially in terms of memory. So to do this, we need to ask the same questions that we did a couple of lectures ago when we are talking about the best fit subspace problem. We have to ask, okay, what does approximate mean? How do I quantify approximate? And what does simple mean? Okay. Depending on your application, approximate can change. Depending on your application, simple can also change, right? And I would say there's more variability in approximation than simple. For simplicity, there is one notion which tends to come up across very, very different domains very often. Okay. So what is this notion? So for us, simple just means that the matrix has low rank. Okay. You can intuitively, if a matrix has rank 1, it's much simpler than rank 2, rank 3, and full rank matrices, right? And again, remember, rank of a matrix is basically the dimension of the span of the rows of X, dimension of the span of columns of X, etc., etc. Okay. These are sort of the standard linear algebraic definitions of rank. Okay. But from a computational perspective, when you talk about representation and manipulating these matrices, the definition that's most useful is the following. So a matrix X has rank less than or equal to R if something happens, right? Definitely the row rank, the column rank, etc. whole, but rank is also captured by something else. Can you tell me what this something else could be? Have X, this is N, this is D. Take a guess. There's so many different notions of rank, ways of defining rank, but one of them turns out to be much more useful for us. Any guesses? Yeah? Exactly, right? And that perspective is very powerful for algorithms, right? The row rank, column rank thing is good for definition and kind of in pure linear algebra. But from a computational standpoint, really, the factorization thing is very, very useful. So the matrix has rank less than or equal to R. If I can write it as A times B, where this is an n by d matrix and this is an n by R and R by D. Okay. So in some sense, I'm writing this complicated looking thing as a product of two simple matrices. Okay. And this kind of this picture itself answers the question of why study rank as a notion of simplicity. Can you think of a notion, of why this might be a good definition of simplicity from a computational perspective? Yeah. Yeah, especially for memory, this can be a huge savings, right? So to store X, we need n times d many parameters. Okay. So imagine, I have 100,000 individuals and their, gene sequencing data, then D is like a billion, or something. Even if you compress it, it's still in the millions, right? So it's way too much, too big to bring it into RAM and manipulate it. Okay. Whereas if I just store the factorization to store A comma B, we only need n times R plus R times D, which is, n plus D times R many parameters. Okay. So imagine something like, just to give an example, n is 10,000, D is 10,000, and R is 2. Okay. Then the difference in storage is almost a factor of like 5,000 or maybe, 2,500. This is huge. Okay. And this, it's not like this is, it's not a problem for current hardware. It's still a problem for current hardware. If you think of large language models, when people do fine tuning on them, they still use this sort of low rank approximations because they cannot have increase of even a factor 2 in the memory. That's way too expensive. So when you do fine tuning, in many cases, you try to do it with a small low rank matrix because I can store it in my memory and manipulate it. Okay. There are other statistical reasons too in some cases, as we will see. But just in terms of computational storage and running algorithms on them, already low rank is a big win. Okay. And as I said, storage is easy. How else can low rank help you? Yeah. Exactly. Matrix operations can be much, much faster, right? And this, in fact, people exploit. You can even be very clever about it. When you add low rank matrices, you have to store the fact. If you store the factorization separately, then your multiplications can be much, much faster, right? It's not just going to save you in storage, but can also save you in time, right? So matrix operations can be much faster. So if I do X times V, for example, that would take me, have a big matrix, which is n times D. I'm multiplying with a vector. This would basically take me O of n times D many operations. Okay. Whereas if I have the factorization, which is A times B, and I want to compute X times V, how should I compute it? I shouldn't just multiply, this is the same as A times B times V, okay? But that's not how I should multiply, never, right? That would be terrible. I should just do it as A times B times V, okay? And the reason this is much better is the same thing happens. I can do this in roughly R times D many operations. And then this in N times D many operations. So overall, I get something which runs in N plus D times R. Okay. And, again, as I said, these are used, these simple things are still used in even very, very modern systems. If you're trying to do long context, for example, people try and approximate the weight matrices with low rank things so that I can just increase the window of the context. That's one of the tricks in the book, not perhaps the most important one, but definitely something that makes some difference. Okay. And finally, there are also statistical reasons. Right? Statistical reasons means at some point, having fewer parameters can be better. Okay. There's this something where, there is a case where over parameterization doesn't hurt you as much, but at some point, having fewer parameters and how you describe your model can help you learn better with fewer examples. Okay. But we're not going into that. We're only focusing on computational things. But we'll give an example anyway. All right. So in that sense, simplicity, capturing or defining simplicity by looking at low rank makes a lot of sense, right? The other thing that we need to do is to quantify approximation. Okay. So meaning I have my matrix X, which might be full rank, and I'm trying to approximate it with some other matrix X tilde, which is low rank. Preferably, we'll just store X tilde as a factorization instead of saying it's just low rank. But how do we quantify approximation? What would be a natural way to define approximation? Just think of the first one and then we'll see. As usual, when you're trying to approximate one vector by another, we can look at the squared error. Okay. So meaning for every entry, we have I equals 1 through n, j equals 1 through d. I look at, the entry-wise error between the two matrices and look at the sum of squares. Again, why sum of squares? Well, if you put an absolute value, things like become really, really heavy, okay? Especially when you're looking at low rank, okay? Squared thing works very well with rank because, it doesn't change when you do rotations and so on. But if I just put absolute values, things become really, really silly. Okay? So even if there are, qualitatively similar things that you can do, choosing the exact cost function is important. Okay, once again, squared thing is much, much better. And this shows up, often enough that it has a name. And it's also an important name that comes from operator algebra, which is, it's called the Frobenius. Okay, Frobenius error, really. Okay, so root mean squared error is defined as sum of squares of this, or the Frobenius error is defined as so just to make it kind of scale appropriately, right? And it's called the Frobenius error because there's a norm for any matrix the Frobenius norm of the matrix, Frobenius norm is just the sum of squares of all of the entries of the matrix raised to the power half. Okay. So that's what Frobenius norm is. All right. So for matrices, there's actually, I would say, Frobenius norm is one very important norm, notion of error. There's a different notion of error that we are not going to discuss, but you can also still solve, is the spectral norm. Okay. And what that means is, we are not interested in matrices themselves, but we're more interested in how they act on vectors. Okay. So perhaps the most important operation with matrices that you can do is multiply them with vectors, right? So I don't, to me, maybe it's important that X actually be close to X tilde, or maybe it suffices that X and X tilde are close in the sense that when I look at the action on a vector, the results are close. Okay. And that leads to a different norm called spectral norm. If you're interested, you should look it up, but we are not going to talk much about it. But the same things will. It's a different way to measure the error between matrices. All right. So with this, we have a concrete optimization problem. We'll call it the low rank approximation problem. Okay. So what's the computational question now? We're given as input a matrix X and some rank parameter K. All right. And my goal is to compute a X tilde of rank less than or equal to K to minimize the Frobenius error. Okay. So give me a low rank matrix which approximates X as well as possible and has rank at most K. K could be 10, K could be 2 or 20 or something. Think of the case where N and D are really big, but K is very small, like, tens or something. Even that is very useful in practice. Okay. We would ideally like even the factorization, but just computing something which is of low rank is good enough, let's say. The way you'll find it is by factorization, more or less. Okay. All right. So that's the definition of the computation problem. Let me now tell you about maybe one of the prominent examples where this played a role. So back in the day, maybe about, say, 20 years ago now, maybe 19 years ago, there was this thing called the Netflix challenge. Do you have any of you heard about it? Do you know how Netflix started? It wasn't a streaming service to begin with. It was this DVD service, right? And one of the things that they had at that time, when I was starting grad school, they had this sort of, basically like an ML competition where they said, I have my users and I have some movies. And their data set was basically, they released something, which is, okay, I have 500 users, 500K, sorry, not 500 users, 500,000. And then I have 17K movies. Okay. And you can imagine that, each user rates some movies. Okay. Not everyone watches 17,000 movies. Okay. So you rate things that you have seen. Maybe I say, okay, this one's a 4, maybe this is a 0, and, this is a 1, and so on. So ratings, think of it as, 1 to 4, 5 stars. Okay. And many of the things have missing entries, really, like, question. Second user maybe rated this movie and this one and this one and this one and so on. And lots of question marks. In fact, most of the matrix would be question marks, really, right? 70,000 movies. So maybe each person rated 100 movies on average. Even that sounds a little excessive, but at least back in the day, because even based on DVDs at the time. So even with that, it's like, yeah, it's a very, very sparse, maybe. Sparse meaning each user has rated only very few entries, very few movies, okay? And then, the actual data set that they released was 100 million. I mean, the size of this thing is 100 million entries, roughly. Like, let's say 500 K times 20K, it's like 100 million entries. Oh, sorry, I think I got that wrong. 100 million entries are seen. Okay, so this is how many ratings that they released. And this is roughly around 1% of all possible entries. Okay, so you have this gigantic matrix of which about 1% of the entries you actually know, right? 1% of the ratings you know. And what is your goal as a company? What could be your goal? What would be very interesting for Netflix? They want your attention, right? They want you to watch more and more movies. So to maximize that, what would they like to do? Well, somehow they want to recommend movies that will get me more hooked, right? So they want to recommend what movies that I haven't seen would be a good fit based on my viewing history, right? You can think of it as a standalone problem where I just have one user's history, but that's, you're missing the picture because you also have all of the user's history. So you want to put everything together, right? So the goal is, in some sense, to guess the missing entries. Okay. And it takes around 8 GB to store the matrix, by the way. 8 GB of RAM. So you can already see that you cannot like store a full rank matrix of this, which is 500 times 220K. At least back with the hardware then. Even now, it's kind of tricky. It's going to be very slow. 8 GB of RAM just to store a single matrix. Now imagine multiplying and doing other stuff with this. Yeah, in fact, there are only 4 values. Even with that, it used to take 8 GB. And when I played around with this on my hardware, I really couldn't. I had to use I could not do it on my laptop in 2006. My memory was basically 4 GB or something, right? So you would store it on your disk. RAM would be 4 GB or something. You would store it on disk and get parts of it or find some other way to work around. Okay. So even with discretization, it doesn't solve this problem. It's just 8 GB entries, really. Okay. And they said, okay, guess the missing entries. And the score would be that the average RMSE on some holdout set. I said this is how typical ML competitions are held. Even Netflix doesn't know all of the ratings. Each they don't have all of the information. But among the things that they have seen, they hide some of the entries. They release some, and they're asking us to guess the missing, right? And they said, okay, we have a basic base model that we've been working with. And the challenge at the time, we'll go back to this challenge in the next segment as well, was the first team to do 10% better than their baseline. They had some algorithm that they implemented. Maybe they looked at geographic locations, age, and some other preferences, and they had some guessing, some way to guess how much each person would like some movie, right? And, they got something like their baseline would win $1 million. Okay, this was the challenge. They had a timeline, like, from the release of the data set, they had about a year for which this would be active, but the first team to cross this would get $1 million. And they had like a, leaderboard for competing and stuff. Okay. All right. Any questions about the setup? Very interesting, right? And one thing that this did, besides this, is really brought out made this notion of Kaggle competitions and everything, sort of outsourcing development, very, very popular and common. Okay. All right. And, there are a lot of, things around then. People looked at, what movies somehow were the hardest to predict. I remember there was this anecdote about movies which are very quirky and sort of polarized ratings. I think Napoleon Dynamite was one of the movies where the ratings would either be 5 or 1. And so those things would be much harder to guess, or at least that was the belief. Okay. And people started looking at, okay, what genre it is, trying to include that information, and so on and so forth. But eventually, just forget everything, just look at it as a matrix, do something that gets you much, much further. Okay. All right. So, this was a challenge. There were a lot of teams competing. It became a huge rat race, and in the sense that, people were teaming up all together. One of the things that got very close was different people applying different methods, and there was like a meta thing that put all of them together. Like 100 different methods just aggregated across, 100 different teams, and that was getting very, very close. Okay. Eventually, there was a team from Bell Labs at the time which won, and they did something, fairly intuitive, and you can in fact explain it in a lecture or something, but I'm not going to do that because that's not our focus. Okay. But the thing that bothered me even at the time was people who designed this, like $1 million, they never took a class on algorithmic ML. I can tell you that because of what I'm going to say. So one thing that many people, you can even check based on what's known, the common belief at the time, and, empirically somewhat verified, is that the true users versus movies rating matrix is actually very close to being lower. Its rank was supposed to be something, with 30, 40 or something. Okay, close. It's not exactly that, but somewhat lower. You can see some structure like that anyway. So the first thing that they should have done, which they didn't, was you pre-process the data to center the scores. Right, so what do you mean by center? Like, if a person likes movies all the time, if all of the ratings that person has is like 5, 5, 5, 5, 4, 4, 4, 3, 3, 3, then the person just likes movies, right? Whereas maybe some other person is like 1, 1, 1, 1, 1. I just hate movies, right? Now, you can adjust for that. Just do some simple correction to center the entries, okay? Instead of them being from, sort of 1 through 5, let's make it like, maybe minus 2.5 to minus 2.5 or 2.5 something, okay? And we don't worry about discretization for now. Just think of them as real numbers. So center meaning subtract the row average from each entry. Okay, for each user, I'm going to subtract whatever the average rating they have for among the scene entries. Okay, yeah. You should. So, that would be the second step. You pre-process this. The variance is not like, at least because it's 1 through 5, it's not like, one person likes 1 and gets 100. So you should correct for the variance too, but it's not as important as this. Okay. If the ratings are between 1 and 100, then definitely variance could also be very important. Okay. So, you should also do that. In fact, people did that too. Right? Step 2 is, sort of scale the variance. Or let's say step, 1A. Okay. Even for this, there are variants like, okay, I do this just for the rows for the users, but then maybe also I should do this for the movies, right? Some movies are just awful. The ratings are just bad, right? That should be the guess. Okay. All this is saying is, given if I don't know much information and ask you to guess the rating for a movie, my first guess should be, how do I actually like movies in general? So what's the average rating so far? I would just guess that. Okay. If I've rated every movie I've seen as a 4, you show me a new movie, I'll say, okay, my guess for that is you'll like it as a 4. Okay. So that's what this is saying, right? Now, step 2 would be, so instead of guessing the average, once I center it, it means that the right sort of first guess for the missing entries would be 0, right? We centered it. If everything was a 5, I would have guessed 5 for the remaining, but I've subtracted the average, so it's like putting a 0 there. Yeah. You can also do that. So you should, there's, again, as I said, tricks to do, should I do just users or just movies? Should I do some combination of the two? You can do both. You can alternate between them as well. They will converge at some point. Okay. But, let's just say I'm doing something very simple now, right? This is one simple thing. And then put a 0 for every missing entry. Okay. And now I get a matrix X where every entry is known. Okay, it's a sparse matrix. That is important because the missing entries are way more. It's only 1%, right? The reason it's important is that I can now store it in RAM. That's a different computational story. But let's not worry about that for the time. Okay, so now I have a matrix which basically says, some numbers are, it looks like this. It's maybe -2, -3, 4, 5, 0, 0, 0, 0, 0. Okay, of course, 0 is just representationally. Most of the 0 really is like my guess for what it would be, okay, after centering it. And then people tried the first thing that I could think of, which is, okay, I have this complicated matrix. How do I guess? They said, I'm going to find the best low rank approximation. X tilde to X for some K. I'm going to pick some rank number K, some parameter K. I'll try different things, K equals 5, K equals 10, K equals 20, whatever. These things, as we'll see, computing them has been known for a long time. We can do this super efficient. Okay. I can do this and then predict according to X tilde. Of course, you have to adjust for the pre-processing. All right. So that's a very simple algorithm. Very classical. This could have been, this is something that's been around for since the 60s and 70s, really. Okay. So I put missing entries, sort of adjust for the means, and then compute the best low rank approximation, and then readjust, right? I subtracted the mean, so I add up the mean, and that's going to be my guess. Okay. So when I do this X tilde, maybe, these zeros will basically become like 0.1, maybe this is like 1, maybe this is -1, maybe this is -0.7, and so on. Okay. Based on this, you can guess, okay, I re-add the weight, the mean, and then I'll get some guess. Okay. So that's, as I said, it's been around for the 60s and 70s. And the first thing that people observed was that if you ran this classical method with k equals 30, remember we have a huge matrix, 500,000 rows, 20,000, almost 20,000 columns. If I ran it with k equals 30, you bet the Netflix baseline by 4%. Okay. So remember, 10% got you $1 million, but they didn't say that 4% will get you 400,000. It was just like all or nothing. But even doing a simple thing gave you a boost over whatever they were implementing in that. Okay. So the minute they released this challenge, I think someone just said, okay, why don't you do this? And then someone did it, and it was like 4%. Okay. So often when we think of these things, low rank approximation can be a first step towards achieving. And the final winning thing is very similar to low rank approximation, but the difference is that somehow you work with a factorization as here, like a times b, but you don't just multiply. You try to put some all kinds of crazy functions and how you reconstruct the entry from the a vector and the b vector. Instead of the inner product, you have some other sort of cost functions. You put some sigmoid there, some exponential things, and then run like basically gradient descent. Okay, so that got you like 10%. All right. So low rank approximation, as I said, it's often a very good first step in many of this, trying to guess missing entries, recommendation systems, trying to find simple approximations of matrices. Okay. So what we'll talk about in the next lecture is, okay, this is a use case, shows how useful low rank approximations are, but how do we compute? Okay. And we'll see how to compute them at scale, in the sense that, this is a case where I can't even store the matrix in RAM, but I want to compute the low rank approximation, right? I can't store n times d sized matrix in RAM, but I might be able to store the matrix with many missing entries. With 1%, I can store 1% entries. Okay. So fortunately, there's like a beautiful solution to both the problems, the best fit subspace problem and the low rank approximation problem that we'll talk about in the next lecture. And there's also a very simple algorithm to compute them. Okay. So that's going to be our focus for Wednesday. And remember, assignment 2 will be out today, and it's due a week from now. And I'll see you all on Wednesday. Okay.